Okay. So let me recap the question for the recording. Laura basically said none of chapter 2 makes sense, is written in gobbledygook, which I sympathize with. So there are a couple of things about this chapter in particular, and maybe the book in general, or less so the rest of the book. There are lots and lots and lots of different models that get used in cognitive science, but some of them have a longer history and are more famous, or some approaches are more famous. And this idea of doing like response time modeling, so visual perception tasks, for example. So this one, I think, is they use some like lines that are going to the left or the right, but moving dot tasks are very common, and that sort of thing. And what you're interested in looking at is modeling and understanding both accuracy and also the time it takes to make a decision. And part of the reason for that, of course, is because a very common thing is to have trade-offs between speed and accuracy. So it's not covered in this chapter, really. It could be covered later on, I suspect. But if you have two sets of participants, maybe one's a clinical group and one's a typically developing group, and in one group you find that their responses are faster, but maybe slightly less accurate than the other group, what are you to infer in terms of their ability to perform this task? Because it could be that they're actually equally good at doing the task, but one group is just choosing to respond more quickly and therefore making slightly more errors. So they're trading off speed and accuracy in a different way. And so it's a classic task for thinking about the different factors that can go into behavior and understanding the origin of behavior as coming from multiple different possible factors and trying to pick those apart in some way. It's also used a lot. And it's also, response time modeling is probably the most developed type of cognitive modeling, I think, in the sense of it's super complex. There's 100 different variations, etc. It's arguably not a wonderful place to start because I think it is a bit niche. Not that many people do the kind of perceptual decision-making tasks that response time modeling is best suited for. And it can, not so much in this chapter, but you can get very into the weeds in exactly what is the difference between these like 20 different evidence accumulation models. But I think that the basic idea of the response time modeling is actually not that complicated. So maybe we can break it down really quickly. So the basic idea is you're performing a task where you're given some visual stimuli and you're asked to make a judgment about, are the dots moving to the left or the right? Are there more orange or blue squares, et cetera, et cetera. And the way that you model that is to say that you're gathering information gradually about the stimuli that you're seeing. And every time you gather a little bit of information, it either points towards one conclusion or the other. And so if you think about how your belief or your evidence is evolving over time, it's like a kind of a gradual slow walk trending in one direction or the other direction, you guess. And then when you've collected enough evidence, when you're certain enough, then you make a decision. And so the idea is you gradually collect evidence for one conclusion or another. When you hit a threshold of having enough evidence, you stop, make a decision. And so that model is explaining both the decisions that you make and the response times in terms of the degree, the strength of evidence. So on average, how big are the steps in one direction or another, and various other noise factors where you start from, that kind of thing, how much evidence you require in order to make a decision, those sorts of things. So that's the basic idea. But I think part of the point of the chapter is exactly about saying, taking that very simple idea and turning that into something precise, either code or maths, involves a number of different steps and a number of different things that might not seem that obvious. And these are the choices that you have to make to go from a qualitative verbal account of how you make a decision to actually a quantitative model. So some of the complexities may be deliberate, I think, in that it's illustrating it's more complicated than it sounds. But some of it's just that unless you do visual perception tasks, it's not something that you're necessarily super familiar with. Yeah, Carsten, no doubt you can add to that.
I wanted to ask back, Laura, was what James was talking about what you found hard to understand? Or yeah, I thought it was probably something else, right?
No, I could understand what they were trying to do, and I could understand, although some of it I was like, because I still have such very, very basic mathematical understanding, I was like, okay, what's vector about it? And then, which you kind of have explained to me, because for me, vector is only just like speed and direction. I can get this, but this other bit, I'm just a bit like, what are you doing? So that was really useful. But there are just other bits of terminology that I think I don't understand why. And like, there's one bit right at the beginning where they say, oh, we created variables that are needed to keep track of the simulation results. And I thought, I don't understand why you need to create this other variable somewhere else to keep track of what you're doing and what the role of these other things are. And I couldn't understand that bit of it. And then there's another sentence which is 0 prepended. And I'm like, nope, no idea. Absolutely no idea. It's just, maybe it's because I don't know, but that immediately makes me kind of shut down and go, I have no idea. And so, I waste a lot of time on that. So if there's anything, that I could be reading somewhere else so that I could come with my little dictionary ready to understand what this is talking about, that would be amazing. But thank you, Carsten. Yes.
I mean, maybe Carsten can. I think so. There's a couple of things going on there. Some of it is, well, actually, a lot of those things are to do with the language that people talk about when they're talking about code and writing code, and some of that varies. Like exactly what you do varies language to language. But I almost feel like, I don't know, that like the best way of getting some of that is actually just working through the code, because it's just a language issue. Like, so prepend is the opposite of append, so it means stick something at the start. That's all it means. Like, it's not but that's like, you go, that's a weird word, that's a stupid word, why would you ever use that word? And then you look at what the code does and you go, oh, it's just putting it at the start. Like, okay, fine. So and the question about like, why do you create a variable to store that's really just the way the computer is working. Is you've just told it to calculate something, and then you kind of have to put that thing somewhere. And so you're creating a variable, a thing, a directory, I guess, to just store the results of something else that you're doing. So again, some of that is just, if you kind of walk through the code, I'm not saying that it all just magically light bulbs will go off, certainly not the first time you do it, but some of it is just about that difference between the way that you might talk about a model in words and the way you actually have to implement it in a computer and tell the computer exactly what you're supposed to do at each step. So, I mean, I guess, yeah, go on, Carsten. Sorry
to interrupt and to usurp the, I don't know, the senior role sometimes. Actually, reading the book, I had the feeling that it is somewhere in a weird middle. So for someone who, like me, who knows most of the stuff except for the details of this exact paradigm, etc., it's a little bit trivial. And for someone who doesn't know anything about it, it doesn't really help getting into it. I also think that the code listings, I mean, maybe that's our style, but many of the variable names are weird, and the way things are done are weird. And then later they change the parameters and run the simulation again. The obvious thing to do would be to put it into a function and call this function with different parameters. They don't do that. So I have the feeling, especially the code, I found very awkward. And but the other thing, yes, I agree completely. There's just some programming language jargon going on, and I don't think there's a dictionary, but basically you would have to learn one language in order to get familiar with these things. So it doesn't matter which of the three languages we were discussing is there. By the way, I didn't get through all of it, but I created Python versions until half of chapter 3. So I was thinking I can either make a new repository, or maybe James, you could give me write access to yours and then make a subdirectory for the Python version.
Yeah, that makes sense. You can just stick it on that GitHub, and then it's all in one place. I'll remind myself to do that. Okay. So yeah, maybe the short answer is, there was a little bit of a discussion last time, I guess, in the last meeting about the extent to which looking at the code is necessary to understand some of this stuff, as opposed to just understanding the ideas. And I always tend to think that you can't really separate the two. And it doesn't matter what code, it doesn't matter whether you think about R or MATLAB or Python or anything, but there's something about actually understanding how it's implemented that is central to understanding what it means. And it's very, very hard to understand what the modeling means without also being able to understanding how to do it. So maybe it comes back to that. So, well, while we're on chapter 2, then, I mean, there's a couple of like fun things in chapter 2 that maybe might get lost if you are focusing on some of the details and the nuts and bolts. One of them, I know whether anyone picked up on this, is this whole thing about they ask a question quite close to the start about okay, we've got this model about how decisions are made and the response times when you don't have a particular drift. So this might be a situation where the stimuli are completely ambiguous and so you can't tell. In that case, you're equally likely to give the correct or the incorrect answer, and the response times will be the same on average for the correct and incorrect. And then it asks this little question about, well, what do you think happens to the response times of the incorrect choice as you make the task easier and easier? So as you increase the drift rate in this time, and it leaves this hanging question, and then it answers it quite a long way later in the chapter. For spoiler alert, if you haven't read the chapter already, what happens is that although you might think that the slower responses, the incorrect responses get slower as you increase or how easy the task is, right? Because on the whole, you're moving in a positive direction, and therefore it might take longer to get down in the wrong direction and make an incorrect response. It turns out it doesn't happen. So actually, your incorrect responses get quicker than your correct responses. And that's what's interesting about that is it brings up a much more general issue than any of the response time stuff we're talking about, which is it doesn't take a lot of moving parts in a cognitive model before your intuition goes totally wrong. And one of the values of actually writing down code and doing this stuff properly in a computer is that your intuition is often a very, very bad guide for what happens in even slightly complicated models. And this is really not a particularly complicated model in this situation, but your simple intuition goes awry. And it happens a lot with me in the models that I use, where sometimes you think that you understand how the different parts link together and how something works. And it could be some idea about memory or something else. And then all of a sudden, before you know it, it turns out the model just behaves completely differently, and the bits interact in ways that you didn't expect, and the data doesn't look like you expected it to. And so understanding, again, the value of actually being able to implement this stuff rather than just talk about it is that very often you don't have a good intuition for how this stuff works. So I think that was like a nice, neat example. And then later on in the chapter, they do this thing, and it's an annoying example because drift diffusion models, evidence accumulation models, are not super popular amongst everyone anyway. But they talk a bit about like the way in which you add in trial variability and how that produces slow errors and fast errors and bits and pieces like that. Again, the more general point is that the model that they start off with is really simple, and everything starts from zero and just drifts in some direction, hits the threshold. It doesn't take a lot of tweaking with that model before you suddenly got lots more moving parts going on, and maybe they've got start point variability, and maybe they've got trial to trial differences in the drift rate, and you very quickly end up not with our model, but with a kind of whole family of different models, depending on the choices that you make at all these different stages. And very late on in the chapter, they show a kind of it's not really like a tree diagram, I guess, of some of the different versions of this basic evidence accumulation model, depending on the different choices that you make about how stuff works. And I don't think there's anything else that's quite has this kind of tree structure quite like evidence accumulation models, but there are lots of other models where there are multiple different versions on it, again, depending on some of these choices. And not all of these choices would have been obvious if you were to verbally describe the model. You probably wouldn't have thought about the difference, for example, between having two different accumulators that head to the same threshold and one accumulator that heads to two different thresholds, but it turns out that matters for something. So again, just a like an interesting example of a more general issue in there. Otherwise, however, chapter 2 is kind of boring. If anyone's interested, again, so the R code's up there, the MATLAB code that I put together reproduces all the graphs and bits and pieces, and you can have a play with it. So if you fancy doing that, go ahead. Otherwise, yeah, maybe not the best example to start a book with, but I guess it serves a purpose. So kind of general stuff in there, and maybe some more conceptual stuff going on along with the kind of the bits and pieces and the specific stuff. What about chapter 3 then? So chapter 3 was the next one, and chapter 3 is kind of interesting because it's the first time maybe people have come across this idea of actually trying to fit a model to some data. So maybe it's, I don't know, did anyone have any questions about chapter 3? I'm a bit like, I'm stuck about how much to go into details of talking about stuff versus how much to keep a broader discussion. I mean, like, I don't really want to go through the nuts and bolts of it, but equally it's kind of reasonably important stuff. I don't know. So, okay.
Hi, can I say something?
Yeah, of course you can, yeah.
Okay, because I read this one, I didn't read.
Oh, you read 3 but not 2. Oh, cool.
Yeah, I thought it was 3 and 4, so I went through these 2 for today. Yeah, I'm a bit lost, I think. I found very interesting that how they start the chapter, and because they're talking about the least squares and maximum likelihood, and how they said that there's no like statistical like background, the first one for the least squares.
Yeah.
And I just, that created a massive void in my thinking. Couldn't understand why.
Well, Carson's smiling, so OLS is a mess, but maybe.
I'm sorry. Yeah, I stumbled across that one too. And the weird thing is least squares is actually a special case of maximum likelihood where errors are normally distributed. So I would say that this is pretty misleading.
Yeah, I mean, it's true, but yeah, okay. It's a slightly misleading thing to say, I guess. I mean, the question is always, though, okay, so like OLS regression makes perfect sense if you have like if you know that your data is such that it's generated from a model, I guess like a linear model in this case, but with normally distributed errors. But I guess the question is like, what happens if that isn't right? Like, to what extent is there anything known about the extent to which the model, this approach will still find a good fitting set of parameters if your errors aren't normally distributed, for example? And it's maybe a little more hazy.
It's just because I thought, like, well, one of the assumptions in psychology is that what you're measuring is normally distributed, and then so I don't know, break all the assumptions about what we like. And ANOVA so far is based on the least squares. So I'm like, is everything wrong so far?
Well, yeah. Well, I mean, yeah. But to the extent that everything is, not everything, but lots of statistics, lots of classical statistical tests are parametric ones anyway, by definition, are based on the idea that you have normally distributed errors. But it's not really, it's such a fundamental assumption that we don't often really question it and think about, is it true, is it not true? And for example, it's very common in a lot of processes in kind of physics or engineering or finance or whatever, that you have so-called fat-tailed errors. So you have much higher probabilities of making big errors than you will get from just a normal distribution. But I don't know. I mean, I don't know. I'm not even sure whether it's an empirical question in some sense, because it's about, I don't know, it's slightly beyond my expertise, but it's a really big assumption. And I guess the problem is that the thing is, once you start actually building models of your own, you get to specify how the errors are distributed, or at least you get to specify how the noise in the predictions according to the model is distributed. And so you don't necessarily need to assume that it's normally distributed anymore. And in a sense, that's the power of modeling, is that you get to go beyond a lot of the assumptions that are made in classical statistical tests. So I don't know, maybe it's a half and half, whether that's a misleading sentence or not. Yeah. The basic point, though, regardless of whether you're thinking about least squares or the other stuff they talk about chi-squared and g-squared and RMS error and other stuff, is you have a model like the models that were discussed in chapter 2 or even chapter 1, where you have forgetting functions and things. Those models typically have some parameters. Okay, so they can make lots of different predictions depending on the parameters. They're just knobs that you can turn, and the predictions change. And the question is, you're trying to figure out what setting of that knob is the one that best reproduces the data you have. And actually, there are two different questions going on there, really. The first is saying, can this model account for the data, full stop? So is this model able to reproduce the pattern of the data that I see? And then almost a separate or subsidiary question is, what values of the parameters produce that best fit to the data? And it's important to separate those two questions out slightly, because a lot of these fitting procedures, regardless of whether it's OLS or maximum likelihood or whatever, will very happily churn away, and they'll give you the best fitting set of parameters, but that might actually not reproduce the data at all. Okay, just because it's the best doesn't mean it's good. So it's useful actually to separate those out slightly. And if your model that you're saying this is how I think the data is being generated, if that's a terrible idea, then there's no amount of parameter estimation that's going to produce something that looks sensible. It'll just produce, it'll do the best that it can. Yeah, but given that you think that the model you have is a reasonable way of generating the data, then the goal for all parameter fitting is basically to find that set of parameters that minimizes the discrepancy between what your model predicts and what the data actually says. And that's what this chapter kind of gets into, with some simple versions of doing that. So it talks about least squares, and we've talked about some stuff. And I generally think that least squares is kind of yucky, but it does have the benefit of being very simple. So it's a kind of nice, simple approach, conceptually straightforward. Dermot, yeah. Oh, you're on mute, Dermot. Still on mute, Dermot.
My excuse is, I'm sorry I joined the meeting late. My excuse for being on mute is because I had my second jab yesterday, so it's beginning to have some effect on me, I think. But anyway, I read chapter 2 and I skimmed chapter 3, and I wish I read chapter 3 in a bit more detail. But just going back to what you were saying, it's one thing to get a set of parameters that goes back, well, that can best fit your data, but how is that going to be any use other than describing the data in a different way? I suppose if given my particular interests, and you get some autistic people and you find that there's, you give them a memory task, and let's say they perform identically to a neurotypical group, which you often find, but yet you suspect there's something very different about what they're doing. And lo and behold, you run your wonderful model building and all the rest, and you get a completely different set of parameters or parameter values or whatever for the autistic people. What does that tell you other than that the parameters are different? I mean, how could you take that off in a different direction?
Yeah, this is a good question. I mean, maybe people have got specific examples if people have some experience of doing modeling in that way, but something that isn't maybe very well discussed in this book, but a distinction that I think is quite useful, is thinking about different possible types of model that you could come up with. So in theory, I guess, you could build a model of how people are making decisions in those tasks that was based on some neurophysiology, right? So some kind of something about, like maybe it was based on neural nets, or basically it was based on something that you believed was a reasonably accurate representation of what the brain was doing at some level. And then differences in those, the ability of those different models to fit the data, or differences in the models, parameters in the models that were fitting the data, you might believe had some genuine basis in the brain. So that's one way of doing it, but that's way too ambitious for most things in psychology. Instead, what you try and do usually is you try and understand the process by which the data is being generated in terms of some like more basic traits or capacities or something of the people, the individuals that you're modeling. So you might have a parameter in the model that represents, for example, something like working memory capacity, or sensitivity to reward and punishment from different situations. And then what you do is you say, well, there might be quite a complicated relationship between the bits of the model that are representing reward sensitivity, working memory capacity, caution, risks taking behavior, whatever. And so hopefully what a model will let you do is it will let you work backwards from the data to say different patterns in the data are potentially accounted from different traits or different characteristics or different capacities of the people that we're modeling. And in the example, so Dermot and I worked on an example not that long ago where we were looking at differences in performance between clinical groups, so ASD and schizophrenia, and typically developing individuals in terms of this particular task. And the story in the literature had been that the discrepancy was due to something. It was due to a difference in the way that people were switching attention between different aspects of a stimulus. And we were able to show with some modeling, actually no, a model where it's actually to do with sensitivity to reward or positive and negative feedback is much better able to account for the data. So here you have an example, not quite like Dermot, because Dermot was talking about something where the data is the same, but here you have data where you have differences in the data between two different groups. Okay, but so what? Like what you really want to know is, you know, what is generating, what's the process that's generating that data? What is the difference between the groups that's responsible for the fact that the data looks different in this task? And you can sometimes do that via some modeling, but that modeling can often be, I guess this is a point I was trying to make, the modeling doesn't necessarily have to be a model of how the brain is working. It can be a model where you try and separate out the data generation process into some other bits, like reward sensitivity or working memory capacity or whatever. And then you look at the extent to which what the data is really telling you is that these different characteristics or traits are differing between groups. So it's letting you hopefully separate out effects of different possible traits or characteristics in terms of things that could be responsible for the data.
Yeah, that's what I find really helpful about it, both in the case that we worked on together, where clearly the groups were performing differently on the Wisconsin card sorting test, but also because lots of times autistic people perform superficially very similarly, but actually when you, in the test situation, test situations are usually quite formal situations where an individual doesn't have a great deal of latitude of performance. But when you put them in the real world where they're supposed to be using the same things, you just know they're performing very, very differently from what you would expect based on their test performance. And even if you can just say, well, it's because they use working memory differently, or because they have some slightly different strategy in accumulating evidence. And if you can quantify that, that's really quite important.
Yeah, I think that's a nice way of putting it. Yeah, you don't have to. I know that's great. I don't have too much to add to that. I mean, I don't think it's super important to talk about the rest of the stuff in chapter 3. If anyone really wants to talk about simulated annealing, we can get into that, ISO.
I didn't get to that.
Yeah, you did. Well, you didn't miss much. So you got your hand
up. Yeah, there's just one thing that really struck me when I read chapter 3, which was the whole discussion about quantitative versus qualitative fits, and how important it is that you verify that your fit is actually making sense on a like conceptual level, and not on a like are the numbers very good and are the fit, like the base factors great or whatever. Like, because you say it, or as they say, you can have parameters that produce a very good fit, but it doesn't necessarily mean that parameters make any sense, or that you can derive any psychological meaning from the parameters. And it also ties into that problem with these local minimas that you can like get trapped in when you fit your data, and you might end up with like a certain set of parameters which works really well, but you might have a completely different set of parameters that might look possibly quite the opposite, which produces a result that is almost equally as good, which might just be like the next local minima on your like surface of your fit. So while reading this, I started wondering whether this problem whether it renders like most of the modeling kind of pointless, you know, because I personally, working with the quantum models, we have so many parameters in the models, and we have so little understanding of the psychological meaning of these parameters, that when I do these fits and I start restricting certain parameters for whatever reason, and I get completely different values for the other parameters, and then I will have to present these parameters and these results, I'm faced with the question, what does it mean? And why can I argue that I can explain the data in two completely different ways? And what does that say about the model that I'm working with? So I kind of lost a little bit of hope in what I'm doing, because I just don't understand how to justify the results that I get while going through the whole process of modeling.
So don't lose hope. So there are a couple of different things going on there, I think, that superficially sound the same, but actually are a little bit different. So some of it's to do with, one of the things you mentioned was, okay, you do one of these procedures, whatever it is, and you get some best fitting parameters, but how do you know that that's really the best fitting set? And this is the thing about local minima, and that's one of the things that simulated annealing kind of helps with. But there are some other issues as well about what if it's not the case that another set of parameters is better, but what if it's the case that there are just multiple choices for sets of parameters that are all equally good? And that's another issue. And those are actually, those are superficially very similar, but actually slightly different. So one of them is about what happens when you have like a very, very complicated likelihood space that you're trying to minimize, or like a kind of a discrepancy space you're trying to minimize. And there are some kind of numerical methods that will help with that, like this simulated annealing, although in practice it might just be really, really hard. And some of that can be remedied by standard stuff in psychology, like, well, maybe you need more data, or maybe you need data from different conditions that will better pick apart these two different parameter sets. But maybe maybe it's a problem with your model. Maybe the model's too complicated. If you have really, really complicated models, then you have viability issues there as well. But this other point is in some ways more interesting, particularly with this quantum stuff, where you can have models where there are many different ways of changing the parameters that lead to completely equivalent predictions. And that's often known as model like identifiability or parameter identifiability. So the issue is that you might have a model that has like loads of parameters that you can set, and then from that it's got to predict some data. And what you want is, if you have a different set of parameters, you get a different set of data. But that's not always the case. And so you have an issue with what's called identifiability or parameter identifiability, parameter recovery, which is basically, is it the case that I can always go backwards uniquely from the data set to a best fitting set of parameters? Or is it the case that there are multiple different sets of parameters that will give me either exactly the same data, or maybe data so similar that it will be incredibly hard, or if not impossible, to pick it apart in practice? And that is less an issue. Well, it is partly an issue to do with the way that you try and fit the data. So there are some techniques that are better if you have this problem with, for example, it doesn't matter particularly what value two parameters have, as long as they're correlated with each other. for example. Like, as long as these two parameters are in a 2-to-1 ratio, I get more or less the same results. And there are some solutions for trying to deal with that with technical problems. But really, I would argue that the more important solution is actually thinking about how you construct the model in the first place. And so if you're building a model, it's always a balancing act between saying, can I include every single possible thing that I can think of that might be important, and every parameter and every change that I could think of, or do I want a model that is as simple as possible while still incorporating the things that I think are super important? And there isn't necessarily a right or a wrong place to fall on that spectrum. It depends on the purpose that you're constructing the model for. But generally speaking, the more complex the model, the harder it's going to be to fit in a technical sense. Like, it might take your computer 3 times as long to run, but also the more likely you are to run into problems like this, and to run into having trade-offs between different parameters, or it not really being clear how to interpret certain parameters. That's another problem as well. But some of that has to go back to how you make it in the first place. If you're building the model and you're saying, this parameter is representing well, some things are easy, like my reward sensitivity. Okay, like, it's kind of obvious how you put that in. But there are other aspects where you're building a model where it just might not be. It's sort of important that you have a parameter in a place, but it's not really clear what it means in some sense. Or it might be obvious from a modeling point of view, but not obvious from a psychological point of view what that means. And some of that happens a little bit in the response time modeling. So this like trial to trial variability in the drift rate, for example, is something it's actually not super obvious how you interpret that on a psychological level, I guess, because you might be looking at literally the same stimuli, but somehow it's important that you have variability in how strong that evidence looks. Anyway, you have more to say on that, Carsten, maybe on like identifiability and parameter recovery, and as if that's a simple topic that you can explain in a sentence.
Well, regarding those questions, my intuitive reaction is your model is too flexible. So basically what James said, yeah. Or to be more precise, it's too flexible with respect to your data. You may need simply more data, or you may need more experiments that can distinguish. Yeah, sorry, I'm repeating what James said.
No, it's good. That makes me feel better. There's another aspect to that as well, which you did kind of touch on, Zoe, which is like the third aspect in this horrible triangle is what happens if you have multiple models that all predict the same data. So this idea of having a model that explains your data falls apart because you have multiple competing explanations that all do an equally good job. And that's another level of hell you can get into sometimes with modeling like this. And actually, response time modeling is a very bad area for having what's sometimes called model mimicry, where you can have multiple different models that like all look quite different in some sense, but they all do an equally good job of explaining the data. And then what are you supposed to do? And some of that we'll get onto a little bit later on in the book, where we'll start to talk about methods of trying to tease apart which model does a better job of describing the data. But some of it is just, again, kind of goes beyond what you can do necessarily by running some code and seeing which number comes out smaller. You need some kind of psychology insight in there as well. Laura.
Hello, sorry, I have another silly question probably, but when you are reading a paper, which I have had to do lots and lots of different papers, and so initially the data shows, okay, there's no difference essentially between, in my case, autistic populations and your neurotypicals, no difference. And then they go through this whole explanation of such and such a model, however, does show that something, 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 in which case I just go, okay, that's fine. How can I, as a reader, know whether it is a unique model? How could I possibly say, as a reader, by reading this, actually, okay, this model fits. However, there's no way for me to know whether another model which you chose not to talk about could equally have fit. Are there some telltale signs of that I could say, okay, that's great, but it isn't precise enough. It could equally be explained by another that you choose not to mention.
I mean, I guess. So mathematically, it's literally always the case that there's more than one model that could do an equally good job of fitting that data. The question is more about whether you care. And that depends partly on how the model's being used, and partly on maybe what sort of a model it is. So if you're proposing a model because you have an explanation that says, I don't know, maybe these 2 or 3 different factors are somehow important for producing this behavior. So these 2 or 3 different traits of a participant are the ones that really matter for producing the particular patterns of data that we see. Saying that someone else could come along and produce a different model with a different set of traits or a different set of relationships between them, or it's something more complex that maybe had a more neural basis or whatever, doesn't invalidate the point that a model with these 3 or 4 different things in it could do a good job of explaining this data. So it doesn't necessarily, I can see Marie in the corner. So Marie and I have worked on something like this where, you know, we showed that a model that has a couple of different features of forgetting and a relative distinctiveness and whatever was able to account for some patterns of the data. It's no slander on the model if someone comes along with a different one and says my different model can also do this. So to some extent, it depends on how the model's being used. But if you're showing that a model with these features can do a good job of accounting for this data, it doesn't matter if an alternative one can. The more general question, though, is if you're saying that your model, the model that you've come up with is somehow the best account or provides a unique account, that's when you're on shakier ground. And I don't think you can ever really say that your model is the best one, or is the one that provides a unique account, or is the one that provides a more parsimonious account, or whatever. But probably in the same way that you would look at a lot of statistics and do a sniff test about, does this explanation look way too complicated? Does it have a million different factors interacting, and that's how you're doing stuff? Kind of in a similar way, if you're talking about really complicated models, or models that seem like they've got a lot of moving parts compared to the data somehow, like you think it's a fairly simple task, but here is this like horrible neural net monstrosity, that might be a red flag that perhaps, I mean, a little bit as Carsten said, like, for example, whether you're talking about your model being, the parameters being identifiable or not, it's not really to do with the model, it's to do with the relationship between the model and the data in some sense. So the more complicated data that you have, and the more interesting patterns in the data, the more you're perhaps licensed to consider more complicated models in order to explain all those different effects, but you don't always need to. But yeah, I don't think there's a single way of doing it, but there are some red flags about models being ridiculously complex compared to the data sets, particularly the type of claims that are being made. Yeah, Carsten.
Thank you, that's really useful.
Maybe one could use the examples they used, I think, in the first chapter as an analogy about the solar system and the epicycles and the ellipses. At the time where the epicycle system existed and was the only model, it worked pretty well. There was not really a lot wrong with it in terms of data description. So what speaks against the epicycle model and in favor of the ellipse model, which is based on Kepler's work? One very important thing is embedding in a theory. And in a way, they both had theories. I mean, the epicycle basically rests on the idea that spheres are perfect objects. So obviously the universe is composed of spheres. And if it doesn't work, then you put spheres on top of other spheres. And the ellipse system is based on Newton's law of gravity, which in other contexts also proved to be useful. So as James said, at a certain point in time, unless you're an expert in that field and you can think of other things and you do the work yourself, there's really no telling whether another model might be better or not. Another thing regarding amount of data and amount of parameters, there are two goals that are sometimes conflicting. If you have the assumption that one of your models is in some sense the truth, or at least could potentially be the truth, which is a hard thing to do in psychology, because probably no psychological model is really the truth, but it makes some sense in other sciences. Then one goal would be to have a model identifying procedure. I think they were going to be talking later about that in the book, about model comparison, this kind of stuff, model selection, where you want a procedure that tells you with the highest possible probability that this is a true model. And then a common goal is if you collect more and more data, the probability to identify the true model goes to 1. The other thing, the other perspective, which is maybe more appropriate in psychology and other sciences where the underlying actual processes are extremely complex and none of your models are probably in any reasonable sense the truth, would be parsimony. So you're using a model in order to summarize your data, and then as James said, the correct amount of complexity of the model depends on the data. This is kind of the other way around, right? In the one sense, you collect data in order to eventually reach the truth. In this case, you construct your model giving the data that you have in order to describe it as well as possible. And again, it depends. This is something, okay, we haven't touched upon that, but you have probably heard of all this machine learning and deep learning kind of stuff. The machine learning people, they come from a different background. Statistics is traditionally very much concerned with finding out truth. Machine learning is more concerned with making predictions. So, for example, you want to have an algorithm that can make an early detection of Alzheimer's. Then you don't really care about whether your model has anything to do with the actual mechanisms of Alzheimer's. What you want to know is, does it robustly predict? And in that case, a parsimonious model might be better because it's led less astray by some noisiness in your data that you can't overcome because you have a limited amount of it. Because, for example, you don't have so many Alzheimer's patients at your disposal. So I think it's important to keep these two different goals in mind when talking about good models.
Yeah, that was a good answer that touched on M open versus M closed universes of models, and also bias variance trade-off without saying any of those words. So good stuff. Yeah, I mean, as Carsten says, some of this stuff we'll talk about a little bit more as we get through the book. But I mean, it's fun because we're only on chapter whatever, and already a lot of the questions that you're coming up with are actually incredibly deep questions about what is the nature of models? What is the nature of theory in a science like psychology? What does it mean to talk about whether theory is correct or not, or is good or useful in some sense? So yeah, I mean, and this is kind of why modeling is so fun in my view, that it's a very fine line between talking about modeling and talking about like philosophy of science. So it's a good window into that. I'm conscious of the time. I want to get people thinking before we break for the day on where we want to go next in terms of what people's goals are for learning about some of this modeling. Because perhaps you're all here because you just can't get enough of Bayes factors and integrals and whatever, but I suspect that the motivation for the majority of people is actually they have a model in mind, or they have something in mind, an experiment that they'd like to try modeling, a paper on modeling that like to try and understand something. And so what I want to encourage you to do, maybe we'll even have breakout rooms, why not, is just try and talk a little bit and try and think about some goals for things that you'd like to achieve. So is there a paper, is there a model that you'd like to implement? Is there something that you'd like to do? And maybe we could spend 5 minutes or so in some small rooms just talking about this, talking to each other about what you might like to do. And then I think for one of the things that I'd ask you to do for next time is actually see if you could maybe bring along a paper or bring along something. And we can start to think alongside working through the technical stuff in the book about trying to implement. And maybe we can get some little groups that meet based on interests to try and think about implementing some models as well. So what I'll do is, and if you need to disappear at 6, that's fine. But what I'll do is I'll maybe just stick us in some breakout groups for 5 minutes or so, and we can have a brief chat and then come back together, and then we can think about the next meeting and what we'd like to do for that. Cool, let's see if we can do this. Let's just Let's just create 3 rooms and then just call it done for that. All right. Well, let's have about 5 minutes just to chat in some smaller groups, and then we can come back together again. 5. All right. See you in a bit.
Okay. We're being recorded. Hi, James.
Hello.
Hi, James.
Your participation is being noted and recorded.
Good, good, good. I'm okay. Okay, so I think I've got an idea, but I was hoping I'd be thrown in with Marie, but anyway, I can raise it with her later.
Hey, I can move you.
No, it's okay. It's okay.
Or I can bring Marie in here and swap me out. Swap out.
Okay.
All right, hang on. Let's see if I can do that.
Everyone wants to talk
You can
about
swap
it.
me if you like.
No, it's all right. I'll swap. Let's see. So maybe I can request that she goes into there.
She may have some other brilliant.
Oh, she's gone. All right. See you in a
What
bit.
happened?
James. All right. Did you swap, James?
Yeah, I swapped.
Okay.
Sorry.
Okay, it was on purpose. Okay.
Yeah.
Just cut Marie off mid-sentence.
Yeah.
I have the power.
Yeah. Maybe I should then start talking about what I was thinking about earlier for a second, because once you're here, it might be worth it. Basically, we have a quantum model going on, and it has that ever ongoing question about what does basically compatibility for different questions mean? How can we interpret the angles of our model, and why do completely different angles result in the same predictions, and what does that mean in terms of the whole basic idea that some questions are compatible, some others are not. So maybe Vasiliki, just to tell you what I mean when I say compatible, we are looking into the question why some people are not able to answer conjunctions, so questions that are about 2 different things at the same time without making really irrational judgments. So basically, if you asked how likely is it that it's raining tomorrow and that the sun is shining, then people start making wrong predictions because they can't conceptualize these 2 things at the same time. And we have parameters that describe to what degree you should be able to conceptualize these 2 things at the same time. And they can vary a lot. So in some results of our model, you can have that people are completely fine conceptualizing these things at the same time, and some other versions you get people are not able to do that at all, and it conflicts and creates weird results. So I've done the fit already, and I get results that are quite promising in relation to other models that are not fitting as well, but the internal consistency of the model that I have is just something that throws me off a little bit.
It's very theoretical. I guess James is one of your supervisors.
Yeah.
Okay.
Yeah, kind of.
Okay. You can point it if you want to discuss about it. It's very, very theoretical, I guess. I mean, do you have context there as a variable? Because compatibility, I guess, matters a lot on the context and timing.
That's a really good question. One that I can't answer at the moment, to be
I
honest.
mean, in a sense, what Zoe's talking about is actually so there's a big issue in all these quantum models. To not talk about quantum models too much. There's a big model issue where this really central component is this thing called compatibility, whatever that's supposed to mean. And one of the problems is we don't really know what it means. And trying to instantiate it in different models and think about the predictions it makes and think about the extent to which it relates or doesn't with other things in the model is a way of trying to understand it. So it's actually, we're talking about modeling in some way as a way of trying to think about the deeper meaning of some ideas and the actual meaning of some concepts that form part of models and theories. So forcing you to actually say what you mean by incompatibility in a particular context and how people might go about assessing that is really, yeah, like it's theoretical in some sense, but it's really about trying to link the theoretical basis of the model with some practical stuff about what people actually do and think and how they behave, and how does compatibility vary between different scenarios and different situations and different sets of predictions. So it's kind of cool in that sense, in that it's not, yeah, it's actually, it's trying to make something that is really, really theoretical actually maybe have more practical value, or make it easy to understand in some sense.
Yeah, I mean, if you find a way to make it exactly more practical and easier to put it in context and use it in experiments and everything, I think it is great. I understand your question earlier on how to figure out what your results mean.
No.
So what's your goal, Vasiliki?
Initially, it was to build a model for the study I'm currently running. But because I have to finish, I finally couldn't. But I still have it in the back of my mind, which is, it was quite complex. So that's why I wanted to have it as a model and not to use the classic mathematical analysis we're using. The idea was basically I have neural data, EEG, and some of them are related to the heart, and how this activity is modulated by visual perception, by embodiment of how we process the stimuli to our own bodies. It was quite a lot of interoception and exteroception integration. And there's a lot of work right now going on active inference models and exteroception, interoception integration. There's a lot of work on prediction with that. And I wanted to see if I can use it there in different groups as well. That had conditions and groups and quite a few different things. So this is what I want to do.
Okay. So is there like an example of a model that does some of this already that you want to work with, or are you building something from scratch?
Right now I'm not building anything.
Sure.
But my plan, and it's still in the back of my head to try and do it at a later stage, is to build it from scratch. Because there are some models already, but I'm working on some new EEG, like event related potential and Boeing specific EEG activity, and all this is quite new. So I don't think I could just get a model from somebody else. Have to be by myself or from scratch.
Okay, cool. We're almost out of time. Stefan, do you have something speedy?
Speedy is in 2 sentences. Probably my goal would be to model loss aversion and the impact of mood on decision making. And there are like a lot of papers already doing that, and I just want to reproduce them. So there has been a whole 7 or 8 papers that use the same model, and I just want to be able to use that model and build it in an experiment and have my experimental setup in a way that I can actually use the data and model it and predict parameters. So that's the goal.
Cool, sounds good.
That's really nice.
Really have run out of time now. Okay, cool, right, let's hop back.
All right. When are we meeting again?
We'll just hop back out to the main room, and then
okay.
We'll try and figure that out.
Because the rest, okay.
Hi everyone. Hey, that worked.
I'm sorry, I was taken out of the room where I was and put into another. I didn't have anything to do with it.
I
It
have
was a
the power. I was in
was
with
a put.
Dermot, and Dermot went, "Oh, I'd much rather be talking to Marie," so I just swapped us around.
No, I didn't say that.
I was mid-sentence in one room and just got.
It's fine.
It's like being on Star Trek and being zapped out of the
Zapped.
room. You know?
Okay. Hopefully we had a chat and came some different ideas. I don't want to get everyone to recap, but it was interesting. Even in the group that I was in, we had one person who was like wanted to do something super practical, fitting and understanding an existing model. We had someone who wanted to build one for some neural data entirely from scratch, which is pretty cool and ambitious. And then someone who was wanting to use modeling to think more clearly about some deeper theoretical issues in the particular area that they're working in. And so that's actually, it's more or less a broad spectrum of different things you can do with modeling. So that's quite cool. Anyone have any like particular insights or ambitious things that they came up with? Like, did anyone want to solve, like understand Carl Friston stuff? Was that your goal? Or?
I want to have more than 2 hours a week to think about anything else but teaching.
Okay,
You know.
Can we build a model to help with that?
Yeah, I don't know. I might get a chance to build something if I actually had 3 minutes to do it.
Yeah, I get that sentiment. Yeah, absolutely. Okay. Anyone else? Did anyone come up with anything particularly? Anyone got any really interesting goals they want to share? No.
Maybe I can report from my group because
Sure.
two of them are gone.
Yeah.
So Rita has a background in forensic psychology, and she doesn't have a concrete project, but she just wants to learn what can be done with modeling and what are the possibilities. Catherine, you can speak for yourself. Sonia is analyzing EEG, and she's thinking of going into multivariate analyses.
I mean, we talked about using the feature model. Well, I didn't say feature model, but we could use the feature model to analyze the dots data that Dermot has. So that might be fun. And I'm really keen to try to get to grips with a whole database I have that I think would need Bayesian style modeling. So I could be wrong about that. It might be something better, might be something else that would be more appropriate, but it certainly has been, people have worked in the area using those types of models, and I'd like to, code my own.
Cool. Okay, cool. Lots of stuff. So as I said, I think I'd send out an email with some reminder for this, but I think a good thing to think about for next time would be to try and do a little bit of research and think about if there is a paper that uses a model that you'd like to understand, or a data set or an experiment that you'd like to think about building a model for, to bring that along for next time. And we can start to think, as I said, alongside the technical stuff, about how we might work together to do some of that. And maybe we can help each other building and maybe implementing some models like this. That might be quite a nice way to get to grips with some of the technical stuff that we're talking about, because by far the best way of learning that is actually just by doing it, I think. So maybe we can try that. So speaking of which, we really are like running late, so we should stop. Lovely to see you all. In terms of the next meeting, I'll probably leave that up to Andreas, but I imagine it will be in a month or 4 weeks or whatever. But we'll send out some details at an appropriate time. If people have really strong preferences about Mondays not being great or whatever, then let us know, and we'll try and take that into account. For the next chapter, we're on chapter 4 now, which is maximum likelihood estimation. It's a big, long chapter, so I think we'll just stick with that one. And it's got the meat in it. I think if you understand how to do this, you can do like the vast majority of modeling that's done. Maximum likelihood estimation is a super widely used parameter estimation technique, so it's a really good one to spend some time and focus on. So let's read that chapter. Let's regroup in about 4 weeks, to be confirmed by Andreas. Please do bring along anything that you're interested in and want to know more about, want to work on. enjoy the sunshine and being outside of term time. And I look forward to seeing some of you soon. Thank you very much for turning up.
Thank you.
Thanks, James.
Yeah, bye.
Bye.
Thanks. Bye.
Bye.